Well, hey, good morning, team. Chemistry coach coming at you. Are you ready? We did gases last semester. We're pretty much done with liquids now. Time to look at solids. All right. So, depending on the class you take and the professor you get, some may go into more detail or less detail. We're going to go through the we're gonna eat the entire Happy Meal, guys. We'll have some fun with it. So I'm just gonna start out with a real quick video just to introduce solid types, and then look at some basics like we did a couple videos on liquid properties. Not going to go in as much detail on solid properties because there's a lot of overlap and what we won't talk about: malleability, ductility, stuff we've looked at before. I want to focus on solid properties in the next video based on intermolecular force strength as we see melting points, sublimation, molar heats of fusion. So we'll do that in a separate video. So this one will be pretty quick. And once we introduce different simple solid types, and simple solid properties, then we can put them all together. We're going to get into phase diagrams. That's putting everything together. And then we'll get into separate videos of very specific types of solids and really open up the hood and look at the engine and take all the parts out and go, whoa, what's going on here? So let's just kind of review what I would do in an introductory chemistry class when I introduce solids. Let's just look at the three most fundamental types or classifications of solids you could have. Really, the most fundamental would be crystalline versus amorphous, right? And we're only going to focus on crystalline solids. So crystalline solids, we'll find out in later videos, have a very repetitive or repeating structure, long range, right? There's something called a unit cell, and you just copy paste in 3 dimensions, and you get this very, long range, repetitive crystalline structure. We call that a lattice, right? Like lattice work. Imagine lattice work, not 2-dimensional, but 3-dimensional. Amorphous solids don't have that long range type of order. So we're not going to focus on amorphous solids at all. We'll just focus on crystalline ones. And pretty simple to break them down. We'll do separate videos for a lot of these based on the particles that make them up. Now, don't think too hard. You ready? Chemistry tough, right? Really tough. Ionic solids. We've already sort of looked at ionic solids when we looked at ion-ion forces. Gosh, what fundamental type of particle do you think make up ionic solids? Ions! Right? Don't make it too hard, my friends. Right? So if you've got cations and anions, boom, it's an ionic solid, right? And I'm going to do a couple separate videos on that. We're going to look at Born-Haber diagrams and all this fun stuff. So, your typical sodium chloride, right? Calcium oxide, aluminum, phosphate, etc. Doesn't really matter. As long as you've got a cation and an anion, you're good to go. And I'll look at each of these separately for maybe a minute or two and then call this a day on this video. But again, we're going to do some separate videos just on ionic solids, looking at what's called lattice energy and stuff. All right, molecular solids. What do you think the particles are in that? If ionic solids are made up of ions, what would molecular solids be? Molecules! Oh! Don't make it too hard. All right, so if you've got these covalent molecules, cold enough, right, where the kinetic or thermal energy isn't enough to overcome the intermolecular forces, they lock into place into this lattice. Boom, you get a molecular solid. Okay, so look at some examples of your typical things. Water is a big one, right? So ice would be a prototypical molecular solid. Dry ice, solid carbon dioxide, right? We still call it dry ice, even though that's a little confusing. CO2, it could even be elements, but they are, like polyatomic elements, like phosphorus. Right? So the phosphorus actually is not individual atoms like in a copper or something like that. It actually exists as these 4 phosphorus atoms bound into this, tetrahedral-like molecule, and then those can interact with each other. We'll talk about that in a little more detail later. And we'll look at the different types of intermolecular forces in between them. All right, so what do you think? What fundamental particle makes up atomic solids? Oh! Play the Jeopardy music. Atoms! right? Atoms, molecules, and ions give you atomic, molecular, and ionic solids. Right? That's what I do in introductory chemistry. So a little review for you here. So atomic solids, right? You could have, if you could get her super cold, you might be able to solidify maybe a noble gas. Be pretty tough to do. You'd have to get it really cold. Metals, right? So, we talked about copper, right? Copper, sodium, tungsten, those different types of things. And we're also going to get into a separate video on what are called network covalent solids. So carbon, silicon, a little bit can form these interesting arrays of atomic solids that we call network covalent solids. I'll do a separate video on that as well. So let's look at each one individually as far as like intermolecular force strength and whatnot. And we'll call it a day on this particular video. Be right back. Let's do ionic solids, which is just a review of the ion-ion forces we already talked about in another prior video. All right, let's review the ionic forces. Remember, ionic bonds. Taken, not shared. Yes, I have a whole room, closet full of dorky shirts. So review that video on when we went through the different types of intermolecular forces. I think the first one I started with was on ionic forces, ion dipole, ion-induced dipole. So look at the ion-ion forces, and we talked a lot about Coulomb's law, right? I give you the equation with that, with the dielectric constant, all that kind of stuff. All you really need to remember from Coulomb's law when you're looking at the forces of attraction between the cation and anion, the higher the charges, because the charges of the cation and anion were in the numerator, right? The higher those are, the stronger the force of those bonds. And since the radius or the distance between the two nuclei was in the denominator, the smaller those sizes are, the closer they get. Remember, the closer they get, the stronger the intermolecular forces. So the smaller those ions, the closer they can get, the higher those forces. So smaller ions, higher charges. I would always look, you don't have to calculate Coulomb's law. You can just compare, for example, potassium bromide and calcium sulfide. Really, you can just compare the charges. You're usually okay with that. I wouldn't look too much at the sizes at this point. Unless they're all like, if it was a +1, -1, +1, -1, then all the charges are the same. So you have to look at the sizes of the ions, right? But if you ever see just, like in this case, potassium bromide, potassium's +1, bromide's a -1, calcium sulfide, calcium's a +2, sulfide's a -2. You can pretty much say that's probably the calcium sulfide will have the stronger intermolecular forces because it has the higher charges. So if you're on a test, you look for that first. But if they're all the same, right, +3, -3, +3, -3, whatever, then look at the sizes. And then again, remember, as you go down the periodic table, they get bigger. So here, if you look at the sizes, if you take the radius of a potassium ion and a bromide ion, add them together, you get 334 picometers. If you take the radius of a calcium ion, which I think is 100 picometers, and add the sulfide, which is probably 184, add them together, you get 284. So obviously these are closer together than those are, and higher charges. So that's going to have much stronger forces of electrostatic attraction. So we can conclude from this that calcium sulfide has the stronger forces. Right, pretty obvious. And then potassium bromide would have the weaker forces. And we're going to look at the impact on properties in the next video. How would that impact melting points? How would that impact solubility? Now, solubilities we're going to do in a later chapter. But obviously, these are held tighter. So if water molecules are going to rip these two apart, which would you say is more soluble than water? Well, that's going to be harder to rip apart. So that's probably more soluble. Right? So you can think about that. And if you look at your solubility chart from first semester general chemistry, you'll see that most of the soluble, when you're forming precipitates and predicting whether it's a solid or not, most of the ones that stay aqueous have the +1 and -1 charges, right? Most of the ones that become precipitates have the +2s, the +3s, -2s, -3s, the phosphates, those kinds of things, right? So pretty straightforward. This is nothing new. We've just reviewed all this. But in the next video, when we look at melting points and molar heats of fusion, we're going to be looking at, hey, you can actually predict which one would have the higher molar heat of fusion, which would have the higher melting point. You kind of look at it. That one's going to be harder to pull apart, right? So you could say this has the higher melting point. Just like we did with boiling points. All right, let's take a look at molecular solids. Pretty simple one, nothing really new there. Then we'll look at atomic solids, be done with this video. Moving on. Let's look at a few molecular solids. And again, mostly review. We spent a lot of this when we looked at intermolecular forces. So if you want to review some of those videos on intermolecular forces, look at the dipole-dipole forces, London dispersion forces, because that's what deal with molecules, right? So is the molecule polar or nonpolar? It's going to really determine the strength of its intermolecular forces. So you can really rank melting points based on increasing intermolecular force strength, right? So a lot of review to be able to do it, but if you know IMF forces real quick, you can just look at it, do it in your head, think of the VSEPR structure, does it have polar bonds? You can tell whether something's polar or nonpolar pretty quick in your head. But these are going to be weaker. Remember, ionic forces, ion-ion, are the strongest of them all, right? So London dispersion forces, dipole-dipole forces, hydrogen bonding are going to be weaker than that. So in general, molecular solids are going to have lower melting points than ionic solids, okay? And it depends how big it is. Obviously, the bigger it is, the stronger the London dispersion forces. But here's some that are nonpolar. Carbon dioxide, iodine, which is a diatomic molecule, right? What's that, decane or something like that. So if those are solids, they're nonpolar, they're only going to have London dispersion forces. So you could rank the melting points just looking at, calculate the molar masses, go from the lightest to the heaviest, the one with the smallest electron cloud to the largest electron cloud. Bigger the electron cloud, the more polarizable it is. So you could literally just calculate molar masses and you can go from lowest to highest melting points, right? You could predict that even if you don't know them, based on only London dispersion forces. Well, here, CH2Cl2, CH3CO, CH3, I think that's a ketone, I think. You got the double bond, carbon, oxygen, double bond, single bond to carbon, single bond to carbon. These are polar, okay? They can't hydrogen bond, but these are definitely polar, so they're going to have dipole-dipole and LDF forces, of course, right? And so you have to look at a combination of, what's their molar mass, how big are they, and how polar are they to be able to rank them. So it's a little more complicated. And last but not least, when you have the OH, the NH, or the FH bond, you've got hydrogen bonding, also with London dispersion forces. So again, you got to look at how big it is, right? But hydrogen bonding is a lot stronger than dipole-dipole forces. So you could kind of eyeball it and get a pretty good idea on ranking intermolecular force strength and thus melting points and whatnot. All right, so let's look at atomic solids. All right, atomic solids, we're going to break up into 3 separate categories, and we'll do a couple of videos for each one. We're going to get in some depth, right? First one, they're pretty simple. I've never run into them, right? But theoretically, if you took noble gases, right, any of the, last column over there, argon, krypton, you name it, doesn't matter. If you could get them cold enough, get them close enough for those very, very weak London dispersion forces to lock into place, you could theoretically solidify them. I personally never seen it that cold before, but I know it can be done. So since they're really, really weak London dispersion forces, they're going to have, you would predict, exceedingly low melting points, like really, really low. I'm not going to do a separate video on those. Pretty simple, right? Just individual atoms, get them cold enough, and whoop, you get that instantaneous dipole-induced dipole, aka London dispersion force. Now, metallic solids, we're going to spend a lot of time on. I'm going to make several videos on just that. So you got your, sodium, your tungsten, platinum, your typical monatomic metallic elements. Now, the simplest way, we're going to look at details on it, but imagine taking, you ever go to the grocery store and you see like oranges stacked up. We think of these atoms as spheres, and if you start stacking them, you stack these oranges up layer to layer, and you see little holes called interstices. We call them interstices. They're just holes. There's a space between them, right? You can't perfectly stack them to fill in all the space. Or if you take you get a small box and pour a bunch of marbles in there. If you picture those metallic atoms as marbles, they stack in there a particular way. We call that closest packing. So we're going to do a video just on closest packing structures, look at kind of the simple different ways that these atoms can form these lattice structures, and based on what's called a unit cell, that repetitive unit cell. Lots of videos. We're going to do that until you vomit, all right? And we'll be able to, from that, if we know how the atoms are stacked in there, we're going to be able to know the distances between them. We'll be able to calculate, the number of atoms per unit cell, the mass of the atoms per unit cell, volume. So with the mass and the volume, we'll be able to actually theoretically calculate or estimate the density of these metallic solids using just the structure, the closest packing theory we're going to look at. It's kind of cool, right? You can compare them to values you can measure in experiments. Neat. So again, going to make a complete separate video just for metallic solids. And they follow a different kind of metallic bonding. You've probably heard of the electron C model, why they're conductive. It talks about certain types of properties. All right, and last but not least, network covalent solids. Hey, if you've got a diamond, right, you know what a network covalent solid is like. It's the hardest substance on the planet, right? So carbon is the prototypical element that is going to follow. It's an atom, right? But it covalently bonds to itself in interesting arrays, right? You get what are called allotropes. We'll look at this in a separate video, but you got diamond, you got graphite, you got buckyballs, those kinds of things. So these act like a giant molecule, right? Not the atoms aren't separated just in interacting by intermolecular forces. They're covalently bonded in this three-dimensional array. So it acts like one gigantic molecule, which tends to make, like I said, diamond incredibly hard trying to break those covalent bonds. But we'll look at diamond and compare that to graphite. Maybe if I have time, carbon nanotubes and buckyballs and whatnot. I'll see if I can find some models. So we'll do that in a separate video as well. All right, so I just wanted to introduce ionic versus molecular versus atomic solids, different types of them, how to kind of, predict intermolecular force strength, because we're going to need to know how to do that to look at and rank solid properties in the next video. Woohoo!